Hello, welcome to our tutorial on outline and shape reconstruction in 2D. My name is Stefan Ohrhallinger from Technische Universität Wien in Austria. I do this tutorial together with Chichu Pitambaram from St. Mary's University in Canada and Amaldev Parakat from the Polytechnique in Paris, France. The outline of these tutorials consists of 6 parts. First part is introduction in the subject and proximity graphs, which are the basis of curve reconstruction algorithms, which consists the second part, then a small Q&A of 5 minutes. Then Amal will continue with the benchmark and demo. There will be a break of 15 minutes. Then he will continue with reconstruction from sketches. There will be a Q&A again, and then for the final parts, Chichu will talk about visual perception of shapes and shape characterization, concluding with a Q&A again. So I will start with introduction and proximity graphs, the third part. So if you look at this image, you might know the children's game Connect the Dots. We have a number of dots, they are numbered, and then you just connect them in order. So this represents the basic curve reconstruction problem, where you might have silhouettes from scans, sketches, medical images, but the principal fundamental problem is you have a set of points and you need to connect them to a shape. Now try to do this without the numbers. It gets much more complicated. But algorithms are still able to do that. However, it's even more difficult for the computer than for us humans. So there's a number of challenges. For example, if points are not equally spaced, because, for example, human vision system follows the Gestalt laws where we tend to connect close points. Also here for sparse sampling we have a feature and there are points which are closer across the shape than adjacent neighbor points. So how do we know that we should connect these points and not the others? For sharp corners, we don't have the information in the point set, so this is something we need to decide with a prior or based on some rules in reconstruction algorithms. Other challenges are if the sample is noisy, for example from sensors. You can see the points are not on the curve. On the top you can see there is a noisy cluster. We cannot even interpolate this with a polygon. So we need to find a way to fit a curve to these samples. We can have outliers, which are given by the blue points on the top here. Outliers are points that we don't want to include in reconstruction. They are not part of the information. We can have multiple curves, meaning that they are not connected in a single outline. Here, 2 nested circles, for example. And curves may be non-manifold, like self-intersections, meaning they have more than 2 neighbors for a point on the curve. In the last 3 decades, a number of curve reconstruction algorithms have been developed, but how can we know which algorithm to choose for a specific problem? Last year, we published a benchmark and survey at Eurographics, where we evaluate a number of algorithms on challenging curves, highlighting their strengths and weaknesses. Here you can see 14 algorithms that we compared with quantitative analysis on reconstruction quality for different aspects and also runtime. Scope of this tutorial, we categorize also 36 curve reconstruction algorithms, for example from boundary samples, but also from area samples where we want to reconstruct the shape, and from implicit curves. An implicit curve is a function in the plane here based on x and y, which is 0 at the boundary and negative inside and positive outside the shape. Or just reconstruct polygonal curves, as most reconstruction algorithms do. We also do a taxonomy of the algorithms. You can find this also in our survey paper. First group is based on graphs, like proximity graphs, that I will talk right after. Then, because point sets may have features of very different size. If you have a very small feature, we need more points to reconstruct than a large feature. So there's algorithms based on the size of these features. They can handle that well. Algorithms which can fit curves to noisy points, which are not interpolating. As you can see in this very noisy example here, how they manage to reconstruct. Also algorithms which can handle sharp corners, which not all algorithms will be able, or non-manifold instead of a polygon. Also there's algorithms which are based on properties of the human visual system. There's the Gestalt laws, where we tend to connect points in our brain based on the properties of closeness, close points continuity, so not changing the angle a lot, and also closedness, because we tend to see closed shapes. Implicit curves, as mentioned before, and region reconstruction. So these are 8 categories. Then we can also classify the algorithms based on properties of the input data. For example, if you have non-uniform sampling, then this determines the feature size that we are able to reconstruct, because we cannot reconstruct features which are smaller than distance between samples. This is similar to the sampling theorem. So we have uniform and non-uniform sampling as a property. Then we have samples which are not noisy or noisy, and then they require fitting instead of interpolating of the points. And we also may have outliers, so this is information which is not relevant or hinders curve reconstruction, and we need to classify, filter that, and remove them before feeding the points to a reconstruction algorithm. Also for the output of the reconstruction, we can classify algorithms by certain properties. We might want to reconstruct a manifold. That means the degree of all vertices is exactly 2. As you can see here, each point has 2 neighbors on the curve. We can relax that to smaller or equal than 2, and then we can also reconstruct open curves. Manifold curves can also be multiply connected. That means it's not a single connected component, so it can be nested, which can represent a hole in a shape. Then output can contain sharp corners, meaning the angle between incident edges to a vertex is smaller than 90 degrees. There's also guarantees. We'll talk about sampling conditions later on. And time complexity is also important. We want to know if we can reconstruct in reasonable time. So for the input capabilities, there's a table in our survey where all the algorithms are listed, and then you can look, for example, you have noisy data with outliers, and it's also non-uniform, and then you can see which algorithms here highlighted in blue are able to reconstruct this point set. We have the same for output capabilities. For example, if we want a manifold output that can have sharp corners and can be reconstructed in n log n time, then we have these algorithms available. Now for some definitions of a curve. So a curve sigma is simple, that means it's not self-intersecting, closed, not an open curve, and planar. We have a second definition which is relevant for sampling conditions. and it has to be smooth. It can be a collection of, so it can be multiply connected, of twice differentiable bounded one manifolds in the plane. Then we define sample set P, so this is a number of n points which are sampled on either sigma or C, and based on these samples we will reconstruct the curve. Here you can see a curve C in black, and then the medial axis in red for this curve. Medial axis was introduced by Bloom in 1967, and the medial axis are all the points which are equidistant to points on the curve, meaning they have at least two closest points on the curve. As you can see here, for several points on larger or very small feature on the bottom, with the circle that touches the curve at least 2 points. Once we have this medial axis, we can also look at the distance of any point P on the curve to its nearest neighbor, nearest point M of the medial axis, and we call this the local feature size, as it tells us something about the size of the feature. So the large blue circle shows a large feature, and the small blue circle shows a very small feature. And then, based on this local feature size, we can specify a sampling condition. Here the epsilon sampling that was introduced by Amenta et al. In 1998. So, in order to be epsilon sampled, a curve has to have all points within a certain distance of a sample. That means it requires a certain sampling density. And that distance is the distance between P and S here, is given as an epsilon fraction of the local feature size of that point. So that means P must not be farther than S, and epsilon times the local feature size. You can see that for small epsilon, this requires a very dense sampling, meaning many points to represent the curve and to reconstruct it properly, and for a larger epsilon you need less points. Since this is features can be very large or very small, and then the spacing of the points, absolute spacing, can be very different. This is not always good for reconstruction because it's often based on distances between points, and we proposed a new definition of sampling where we take the interval along the curve of 2 points. So instead of taking local feature size at the point P, we take the interval between P0 and P1 and define the reach of a curve interval as its smallest local feature size in between. Then, similar to the local feature size, as at point P we have the reach for this interval, and then we can say that row sampling, we proposed it in 2016, so a point has to be within a sample of a distance row fraction of the reach of P. So this is similar to a local feature size, but later we will see that this has advantages in how many points are required to sample a curve in order to reconstruct it. Next are proximity graphs for a point set. Here you can see 4 proximity graphs starting with the minimum spanning tree, and these are all subsets of the graph on the right until the Delaunay graph. So the minimum spanning tree, also Euclidean minimum spanning tree or EMST, is a graph that is free of cycles. It spans P, that means all points are connected, with minimum edge weights, that means total edge length is minimum. And we can reconstruct this graph, for example, with the Dijkstra algorithm that takes all the edges of the Delaunay graph, which you can see on the right, and adds edges starting with the ordered by length, so starting with the shortest edge, and adds edges to the minimum spanning tree until all vertices are connected and in a single component. Next is the relative neighborhood graph. Here an edge is included if the circles at its two endpoints with the radius of the edge length do not contain any other points, as you can see here. And this is a subgraph of the gay-value graph. And edges in the gay-value graph if the empty ball centered at an edge is empty of other points. And finally, the Delaunay triangulation has the property that circumcircles of triangles are empty of other points. So these proximity graphs are useful for constructing graph reconstruction algorithms. There are some other proximity graphs, so we show next. So we learned about the Euclidean minimum spanning tree. Euclidean means that it's planar, basically requires at least one incident edge per vertex, so degree is larger or equal than 1, and then it spans all the vertices. So this already can see the shape more or less, but we proposed in 2013 the boundary complex, where we extend this criterion to a degree of greater or equal than 2. And we do this by adding edges, similar to the minimum spanning tree, in order of increasing edge length until all vertices have at least 2 edges. And I can see that this resembles already much more a shape. And it's also closed, so we have an interior shaded yellow. It's deflated at the bottom somewhere, so it's not there yet. But this will help in reconstruction, as we will see in the next part. Then we have the sphere of influence graph, which was proposed by Toussaint in 1988. Edges are in the sphere of influence graph if the spheres with radius of the distance to its nearest neighbor. So we have these spheres or circles in 2D for each point. And if the spheres interlap for 2 points, then we take that edge as in the sphere of influence graph, as you can see here. And finally, there is a proximity graph called the shape hull graph, which is already reconstruction. So here we take the Delaunay triangulation and we subtract divergent concave triangles. The intuition is that concavities are removed, and so this is work published by Jicho in 2015, and this can already reconstruct a certain class of shapes. So this concludes the first part, and next we will continue with reconstruction algorithms.